you how we designed our anti-theft device and the circuit design process. My name is Fernando. He is Jason. You are Jacob, and you are Scott. You're Peter, and you are. You are.
He isn't. You are. Also, the learning process. Throughout the week, we had several learning process to go through. So the principles we need for this project is basically the truth table, knowing the differences between the and NAND gates, the inverters, how to make the breadboard and how it is organized and stuff. And so we had lectures over the course of the week, and also we had a project to get us used to the information we received. So the project was the college accepting whether you make it into the college or not, the circuit that we made earlier. So we had, in that circuit, we had to address the question that if either you take the SAT or the ACT, and you have to take geology and psychology to make it into college, and that helps us get familiar with the and or gates, because the logic equation would explain where to use the and or gates. So this is basically the video that we took and demonstrating our circuit.
Worked on the circuit. Jacob and Scott worked on the Prezi, and Tan and Peter worked on the webcam.
I was also taking photos throughout the process.
Yeah, also as a group, we all worked a little bit on each other's stuff. We all did everything kind of as a group effort, but generally those were the main roles.
Yeah.
Alright, so the first part in our design process for the circuit was the truth table. And in order for us to get a good understanding of what we were doing, we made sure we had our 3 inputs and all our outputs figured out, because there was a certain process that Professor Gray made, so that way not all 3 LED lights would be on at the same time. And so here's our 8 different inputs and 8 outputs. So from the truth table, then we got an equation which allowed us to draw an actual logic circuit, and so that way we would understand which certain AND gates and OR gates to put into certain places. And then this also allowed us to put it into Yenka. This allowed us to put it into Yenka so we could actually simulate it and then actually see if the design we had would actually work if we actually redid it on the actual breadboard. Oh, here's actual design that we made on Yenka, and you can see the different AND and OR gates going to the different LED lights and the buzzer. So yeah, we made it work on Yenka, so then we made it work on the breadboard.
Okay, this is our alarm circuit. The circuit that was in the lab manual, it didn't really work for us because we couldn't supply enough voltage to it. So I worked on the computer with the 5x5 timer simulator and created this circuit to have the alarm sound.
Yeah, so we built the initial circuit for the alarm based off of the 1 in the diagram, and we ended up, as we'll show you in a bit, we ended up using a separate power supply for too weak to turn on the alarm alone, but combined with the power, the 9 volt power going to the logic circuit, it would be enough power as well. And that also fixed our problem of having too much power going to the whole circuit, the logic circuit, which would keep some lights dimly lit when they were supposed to be off. And it made it also safer on the chips because you're not putting tons of power through.
And so we had to do trial and error for that. Like, we tried with 18 volts on the main power, and those kept the LEDs on. And then we tried the new way of putting the battery in series with the alarm in the logic circuit, and it works well.
So when we designed a completely different alarm circuit, then we started on the physical construction of the breadboard. And I think Scott and Tan worked on the alarm circuit, and then Fernando and Jason worked on the actual breadboard. And that just started construction.
So this is a video of me working on it. And then during the process, at first I didn't use a map of the breadboard, and then eventually after like the first 2 LEDs, the third one got really confusing. So I started to write out the mapping of the logic. And that's our final part.
Our final product, we started by setting that the switches would send a 0 input if they're on and a 1 input if they're off. So with that being said, we basically connected the three switches to an AND gate, so it will light the green LED. For the yellow LED, it was pretty harder because we had to pass one of the switches to an inverter. So when it's on, it would send a 0 input, but in the inverter it would send a 1 input, and then we pass those through an AND gate, and that would be like a final input, and we have to do that 2 more times for the other 2 switches, and those 3 final outputs will be input of an OR gate, which is meaning that if any switch is activated, the yellow line will actually light up. And the same thing for the red light, but instead of using 1 inverter, we use 2. And the alarm circuit actually was the easiest one because we just had to pass the 3 switches to an inverter because we said that off was 1 and on was 0. So when all of them were on, they would send a 0 power, but if we pass the 3 of them for an inverter, and then it will actually light up, activate the alarm circuit.
Okay, so we're gonna circuit. The green light's on now. 1 switch, the yellow. All the switches work for it. And then 2 for red, and then 3 for the alarm. Maybe.
Yeah, I heard that.
Okay,
Loose wire.
that's the alarm. Yeah, that's just a loose connection on one of the inputs. So that's a fairly easy fix. No circuit. Okay. That was one of the challenges we had when we were working through it. And then also, as we were working, like that alarm circuit was a pain to work with because it would always not work, or it'd be like inaudible. And then also, I was working on the logic, so I used more chips than probably was necessary because some of the inputs, say like for an inverter chip, here's the chip with the inputs. Here's the positive power, here's the negative power. The input would be here, so like the A input would be there and the A bar would be here. But there's also the 3 other slots in the breadboard, which I could have wired the other things that need to be inverted to, but I think I used another inverter chip instead of just using that same output.
we finished the circuit and we learned a few things like teamwork and organization is vital if we want to finish the device on time. So as Scott said, we worked off of each other, which meant that we had 3 or 4 people working on one thing like the circuit or the Prezi, and then we had like 2 other people just working by themselves. So there's an unequal distribution of work. And then we also learned that we should plan first before we use Jenga or start building, because we first used Jenga and then it started getting really messy, and then we started using our tree table, so yeah, it's pretty bad. And then how we would start a project differently, as I said before, we should start planning first instead of trying to simulate the circuit, because the tree table